can you believe it, 4 videos on these topics. So here are 2 examples of histograms of data for a rather small data set. One of them has 20 individual bits of data, and the other has 25. Notice both of them are less than the 30 that we're aiming for. So are these normally distributed or not? Remember, this is Minitab, and this is what Minitab chose to do with the data. Maybe if I chose different bins, it would have come out differently. That would be a little bit difficult with the one on the bottom, since we're counting heads, the customer's heads, that is. For the top histogram, we could choose different bins for the O-ring thickness, cut them off at different intervals, and the graph might look a little bit different. But is there a way to do this other than just eyeballing it? The answer is yes, there is. All right, I'm going to try to move this off to the side. We may want it a little bit later. One of the examples in your book has to do with an auto repair shop and a record of the number of customers. And those are daily customers. I am not going to work with all 25 of the days on which the customer number was recorded, but I will do 8 of them, 24, or 26, 24, 21 on another day, 25 on another day, 26, 24, 1, 2, 3, 4, 5, 6. I need 2 more, 25, 26. Yep, and 25 and 26 are the next ones. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 individual data points. To do this by hand, I will have to put them in ascending order. So let's see, 21, 24. 24 shows up again. 25, 25, and 3 26s. And now I must introduce a new formula. Unfortunately, this course is not involved enough for me to derive this formula for you. You don't have quite the skills you need to do that. So I'm afraid you're just going to have to take this on faith, that this formula will give you the area under the curve for x sub I. So for the first data point here, once we've put them in order, if you plug what's necessary into this formula, it will give you the area under the curve to the left of the data point 21. And under the curve, it's the normal curve we're talking about. So when you look at these, remember that the index is just what number each data point is in the list. So the index of 21 is 1. Here's 2, 3, 4, 5, 6, 7, and 8. So for 21, we have the index f sub 1, okay, because that's the first data point. Okay, in place of the I, we put the 1, minus 0.375 over, how many are there total? There are 8, plus 0.25. And what does that give us? That gives us 0.075, or when it is rounded, 0.08 or 8/100ths. If you perform the same calculation for each of these numbers, you'll notice that the only thing that changes is the I, is this first number. The n is the same for all of them. All the numbers remain the same. Only that first number changes, because it's only the order that we're interested in for our purposes right now. So there's the calculation performed for each of those. Why is the index the only thing that changes, that first number in the formula? Well, we're lining these up in ascending order. And so the lower numbers would be the lower part of our normal distribution, or our standard normal distribution, and the higher numbers would be toward the upper part. So we would expect that the only difference in what the outcome is would depend upon where it is placed along this graph, this distribution. So we put our data values in order. We performed this calculation for all of them. What next? Since each of those numbers represents an area, probably should have done this in a different color. But there are the column headings. This is the number of customers. This is the area associated with that data value. That's the area to the left of that data value on a normal curve. And then we have to refer to our z-table to find the corresponding z-score. So we're going to go from here to a z-score. So I'm looking for a 0.08 here inside of this z-table. So 0.08. So I'm looking down through all the numbers, and I'm looking for something as close as I can get to 0.08. And what I see is I have something very close to it here. I have 0.0808 and 0.0793. It happens that the second one is just 1/10,000th closer to 0.08 than the other, so that's the one I'm going to use. Therefore, I look left, and I grab this negative 1.4, and then I have to go up. So I get a 0.1. So I have negative 1.41 is my z-score. All right, and if I do the same thing, I hunt for 0.20 now. Inside this same table, 0.20. Let's see, 0.2119, 0.2148, 0.2090, 0.20, so getting closer and closer. These two numbers are very close to 0.20, but this one's a little bit closer, so I'm going to go across the row and up the column to find out what my z-score actually is. So let's do that. Let's shrink this in some. And okay, here is my number right here. Okay, if I go over this way, I have negative 0.8, and if I go up this way, I have 4. So that z number is negative 0.84. So let's get rid of those. Whoops. Didn't mean to get rid of my z-score. Gotta bring that back. And here are all of the z-scores that correspond to our calculated areas. Now that we have the z-scores, we combine those with the original data. And let's move these scores over. So they almost line up. Might need a little indication here which goes with what. Okay. All right, now that we have that, we can actually graph this thing. Because what we have is an ordered pair in each case. For instance, the first ordered pair would be 21 and negative 1.41. So could we graph that? Yes, and we are going to. Okay, let's graph what we have of ordered pairs here. Here's my graph. Now, I'm going to graph 21 and negative 1.41. Then I will move over to 24 and negative 0.84. There. My next point is another 24, but it is located at negative 0.47. So about there. Then I have a 25 that is located at negative 0.15. I have another 25 that's located at 0.15. Let me move this over so we can graph the rest of it. Let's see, I have my two 25s and I have three 26s. Let's remember where those go. Those go at, whoops, I forgot already, 0.47, 0.47, 0.84, and 1.41. 1.41, so somewhere around there. Okay, so what does that look like? A little bit of a mess there. And remember, that's just 1, 2, 3, 4, 5, 6, 7, 8 points. 8 coordinate pairs, which is what I started with. So I have everything graphed that I was supposed to. Is it approximately linear? Could you go in there and find a line of best fit? Yeah, you could. That looks pretty good. How could you know if there is actually a linear correlation between the original data values and the z-scores for those values? Yep. You could find a correlation coefficient. You could check it against the critical values listed in the other table that you've worked with before. You could find the equation of that line, and you could find the coefficient of determination. And analyzing all of that, you could see if there's a linear relationship. You'll be glad to know there's an easier way. It's called Minitab. Let's shrink all this down and move it out of the way. So here is the probability plot of the full data set for these number of customers at this auto repair shop. And those are numbers of customers daily. When you have calculated your mean and your standard deviation of a data set, you can put that information into Minitab. And, the mean and the standard deviation really are not useful unless it is normally distributed. So you can either go through doing a histogram and seeing what it looks like, finding your median, comparing it to the mean, maybe doing a box plot, or you can put that mean and that standard deviation along with the data set into Minitab, and boom, you get your probability plot. And what this probability plot says is that if all the data is within the bounds, these outer red bounds here, then we can assume it's normal, even if it is a small sample. But look at this. That dot is outside of the bounds. Therefore, the number of customers daily is not normal. Actually, the number of daily customers might be very normal for this business, but the distribution of the number of customers is not normal. It's not a nice bell curve. Let's look at the probability plot of the other data set that we had a histogram for. This is the probability plot of O-ring thickness. And if you look along those boundary lines that Minitab so nicely puts up there for you, you'll see none of the dots are outside of the bounds. And instead of saying normal, the data is normal, it is, yes, better to say the data is normally distributed. Okay, but this is statistics, so we're always noting that we don't know everything. So we say it's approximately normally distributed.